traveling through space seems to be the next natural step for humanity. After all, we have already conquered the skies, crossed oceans, climbed mountains, and even created machines that soar above the clouds. So why are we still stuck here on Earth?
The truth is, space is immensely hostile. It does not forgive mistakes. There is no oxygen, no gravity as we know it, and everything out there, from radiation to the lack of pressure, seems intent on destroying us. In over 60 years of space,
exploration, the farthest a human has ever traveled, is the Moon, only 384,000 kilometers away. That may seem far, but in cosmic terms, it's practically around the corner. So why haven't we gone further? Well, even that small step was an extraordinary feat of engineering, courage, and luck. Apollo mission astronauts traveled in capsules with technology inferior to a modern cell phone, facing risks that today seem unimaginable. Enormous effort, billions of dollars, and global political drive were required just to touch the lunar surface. And even then, we have never returned since 1972. Now imagine traveling to Mars, a planet on average 225 million kilometers from Earth. A one-way trip could take 6 to 9 months, if everything goes right. The challenges are countless. We need to protect astronauts from solar radiation, provide food, water, oxygen, waste recycling, delayed communication, psychological support, and an emergency system in a place without hospitals or rescue. And what about the return? That is another story. If anything goes wrong, they will be completely alone. But what if we look even farther, beyond our solar system? Proxima Centauri B is an exoplanet orbiting the closest star beyond the Sun. It is only 4.2 light-years away. This means that if we traveled at the speed of the fastest spacecraft ever created, it would take over 70,000 years for a one-way trip. This is why, despite all the advances in science and technology, space remains our greatest challenge. It is the final frontier. And to cross it, we need far more than powerful rockets. We need revolutionary ideas of global cooperation, courage, and time. With that in mind, today's video explores the barriers that prevent us from going beyond Earth. We will examine what makes space travel incredibly difficult, what we have already overcome, and the plans, some realistic, others purely theoretical, for one day leaving the cradle of humanity to become, truly, an interstellar species. But before we start, it's important to clarify that everything involving space travel is still highly speculative. Much of what we will see next has not even left the drawing board. We will take the liberty to conduct some mental experiments, attempting to visualize what an interstellar journey and life on an exoplanet might look like. That said, fasten your seatbelts, because our space journey begins now. Have you ever wondered why, with all our current technology, we still haven't crossed the limits of the solar system? We have reached the Moon. We have sent probes to the farthest regions of space. But beyond the edge of the solar system, nothing. Are we trapped in our cosmic bubble? From the first steps on the Moon to the daring explorations of the Voyager probes, humanity has ventured beyond our home planet. Yet when we gaze at the stars that dot the night sky, one question arises. Why haven't we advanced beyond the limits of our solar system? Technologically, we have made giant leaps. We have built rockets that defy gravity and telescopes that capture images of distant galaxies. But when we try to go beyond Uranus and Neptune, we encounter challenges that remind us of the enormity and complexity of the cosmos. The speed of light, our current measure for vast distances, imposes severe limits on our current exploration. So the question remains, is it truly impossible to leave the solar system? Will humanity ever achieve this incredible feat? To understand why leaving the solar system is so difficult, we first need to measure the colossal size of the system we live in. When we talk about the solar system, we are not just referring to the planets and their moons. It also includes asteroids, comets, and above all, the vast region known as the Oort cloud, which may extend up to 100,000 astronomical units beyond the Sun. One astronomical unit equals the average distance between the Earth and the Sun, approximately 150 million kilometers. This means the solar system can extend up to 15 trillion kilometers. Can you imagine how enormous that is? This size is so vast that even the fastest spacecraft ever built by humanity could only traverse a small fraction of it. For perspective, Voyager 1, launched in 1977, has been traveling for over 45 years at nearly 61,000 kilometers and has barely left the heliosphere, the bubble of charged particles emanating from the Sun. Even so, it has not yet reached the edge of the Oort cloud, meaning it is far from completely leaving the solar system. This reveals a harsh truth. Our current technology is far from capable of exploring even the outskirts of our cosmic neighborhood. Even sending a signal or a spacecraft to the outer regions of the solar system would take thousands of years. At current speeds, it could take over 30,000 years to cross the entire system. But it is not just distance. There is also the energy problem. Physics laws are clear. For a spacecraft to fully escape the solar system, it must reach a certain speed to overcome the, say, Sun's gravity, which at Earth's orbit is about 42 km/s. The fastest manned spacecraft ever built, Apollo 10, reached approximately 11 km/s, less than half the 42 km/s needed to escape the solar system directly. It's not that we don't want to leave, we simply cannot. Our system functions as a cosmic prison, with invisible walls that are incredibly difficult to cross. Every kilometer away from the Sun represents a battle against immense distances, lack of energy, and the limits of current technology. Surprisingly, even our most advanced spacecraft are not designed to fully escape the solar system. Why? The answer lies in fundamental physics, fuel limitations, and the extreme difficulty of maintaining such high speed over long periods. To leave the solar system, a spacecraft must exceed the Sun's escape velocity, which varies with distance from the Sun. At Earth's orbit, it is approximately 42 kilometers, or around 150,000 km/h. Achieving this speed requires tremendous energy, far beyond what any conventional manned rocket can provide. The Voyager probes escape the solar system using a crucial aid, gravitational assists. This maneuver uses the gravity of giant planets like Jupiter or Saturn to gain momentum and accelerate without using extra fuel, a cosmic slingshot. This is how the Voyagers reach speeds near 61,000 km/h, enough to overcome the Sun's gravitational pull. However, these missions were unmanned and extremely light, carrying no life support, radiation, shielding, or extra fuel for a return. Everything was optimized to reduce weight and maximize acceleration. A manned spacecraft would require tons of additional equipment to keep occupants alive for decades or even centuries, greatly increasing weight and energy requirements. Moreover, the Voyagers had decades to reach the outer solar system. A manned mission cannot last that long without radical advances in cryogenics, resource recycling, and energy generation. Current spacecraft are simply not designed for interstellar missions. Chemical propulsion, though effective for near-Earth or Mars missions, cannot provide the sustained thrust needed to escape the solar system permanently. For now, our best spacecraft barely scratch the limits of our solar bubble, and always without humans on board. To go further, we need new technologies, new materials, and above all, a revolution in how we conceive space travel. In 1977, humanity launched two of its most ambitious space missions, Voyager 1 and Voyager 2. These probes were not just designed to explore the outer planets, but also to venture into interstellar space. More than 4 decades later, both continue traveling in straight lines, moving steadily away from the Sun's influence and writing a story no other human-made object has matched. Voyager 1, the faster of the two, is the farthest human-made object from Earth, over 24 billion kilometers away, traveling around 61,000 km/h. Voyager 2 moves at approximately 55,000 km/h, more than 19 billion kilometers away. Both have left the heliosphere, the magnetic bubble formed by the solar wind, and are in what astronomers call interstellar space. Although they have not entirely left the solar system, you might wonder how they can be in interstellar space and not have left the solar system. The technical boundary of the solar system is not the heliosphere, but the Oort cloud, a spherical shell of comets and debris extending up to 15 trillion kilometers. At current Voyager speeds, it could take over 30,000 years to cross this invisible frontier, and they would likely stop functioning long before reaching it. But the Voyagers are more than scientific probes. They are messengers, carrying the famous Golden Record, an interstellar message created by a team led by Carl Sagan. The disk contains greetings in 55 languages, Earth sounds, music from around the world, and over 100 images representing our planet's diversity. The idea is simple and powerful. If an intelligent civilization finds the probe, even after humanity has vanished, they will know we existed. In other words, the Voyagers are time capsules launched into the void of space. They seek no destination, only wandering, crossing the infinite darkness. They are the silent cry of a species confined to its star system, yet daring to reach for the stars. Traveling to another star has been the ultimate dream of astronomers, science fiction writers, and visionaries for centuries. Making this dream a reality is one of humanity's most complex tasks. The big question remains, will we ever achieve it, or is it entirely impossible? The closest star to the Sun is Proxima Centauri, about 4.24 light-years away, roughly 40 trillion kilometers. At Voyager 1 speeds, it would take over 70,000 years to reach it. Clearly, we need a new type of propulsion. Fortunately, some projects are exploring new technologies. Starshot, for example, proposes sending small chip-sized probes at up to 20% the speed of light, using solar sails powered by powerful lasers from Earth. If successful, these microprobes could reach Proxima Centauri in just 20 years. However, they cannot carry humans, and the infrastructure for large-scale launches does not yet exist. Other concepts include nuclear propulsion, like the Orion or Daedalus projects, using controlled nuclear explosions to propel massive spacecraft. Fascinating, but extremely complex, expensive, and ethically and technically challenging. Even more theoretical, ideas, such as fusion engines or warp drives inspired by science fiction, remain largely unrealized. Despite these concepts, we are still far from reaching the stars. No human project currently approaches sending a manned spacecraft beyond the solar system, let alone to another star. But science advances, and what seems impossible today may become tomorrow's reality. Imagine a future where humanity leaves the solar system not as robotic probes, but as a conscious civilization, crossing the boundary of its cosmic cradle. Such a moment would mark a turning point in our species' history. Leaving the solar system would be not only a technological achievement, but an existential statement. Reaching this milestone would mean mastering large-scale energy generation, cosmic radiation protection, human hibernation, and life support for decades-long journeys. It would also imply the ability to build self-sustaining spacecraft capable of interplanetary and interstellar travel, a socially, intellectually, and technologically evolved humanity. Yet this dream has a harsh side. Leaving the solar system will not be for everyone. Initially, only a few pioneers may succeed, possibly living and dying aboard spacecraft without ever seeing another sky. This will be a one-way journey, a leap into the abyss, an adventure with no guarantees, but also the greatest act of faith and courage our species has ever undertaken. As the colony grows, genetic policies begin to be carefully evaluated. With the constant risk of hereditary diseases and inbreeding among the descendants of the original colonists, strict guidelines are established to preserve genetic diversity. Genetic material from Earth is introduced, strengthening the population. The debate over genetic engineering remains intense. Some argue that modifying humans to be more resistant to radiation, stronger or better adapted to the local gravity, is essential for long-term survival. Others insist that tampering with human genetics crosses ethical boundaries and risks losing our connection to humanity's origin on Earth. By the end of the first decade, the colony has established a functioning society. Education systems are implemented to teach the younger generations both Earth history and survival strategies for the alien environment. Cultural practices evolve, blending Earth traditions with innovations necessary for life on Proxima B. Social hierarchies emerge naturally, influenced by technical expertise, leadership abilities, and adaptability to the harsh conditions of the planet. This new society must balance progress with sustainability, ensuring that the exploitation of resources doesn't jeopardize the fragile alien ecosystem. The technological advancements continue at a rapid pace. Power grids fueled by nuclear fusion and geothermal energy support vertical farms, water purification systems, and life support habitats. Engineers and scientists collaborate on constructing large-scale infrastructure, including transportation networks across the uneven terrain, radiation-shielding domes, and emergency shelters for solar flare events. Medical facilities advance as well, developing treatments for radiation exposure, muscle atrophy, and respiratory illnesses caused by the planet's toxic atmosphere. Telemedicine systems allow specialists aboard the orbiting mothership to remotely support colonists in real time. Despite these advancements, psychological challenges remain a constant concern. The endless twilight, the alien sky, and the isolation from Earth weigh heavily on the colonists' mental health. Programs of light therapy, exercise, meditation, and virtual reality simulations of Earth environments are used to combat depression, anxiety, and the feeling of detachment from home. Families work together to maintain social cohesion, creating rituals and routines that provide stability. Interpersonal conflicts occasionally arise, but conflict resolution committees ensure they are managed before escalation. Exploration of the planet continues with the aim of securing future expansion. Scouts map the terrain for additional resource deposits, safe landing zones, and potential sites for expansion of the colony. Experiments in soil enrichment, artificial pollination, and hybrid plant cultivation are underway to create a sustainable food supply capable of supporting tens of thousands of colonists. The colonists learn to harness the unique properties of the planet's environment, using its minerals, ice, and geothermal activity to solve engineering and energy challenges. As the century progresses, humanity begins to understand the delicate balance between adapting to Proxima B and modifying the planet itself. Terraforming experiments start on a small scale, testing atmospheric adjustments, temperature regulation, and chemical stabilization techniques. Meanwhile, debates continue between those advocating full terraforming to replicate Earth conditions and those preferring adaptation to the native environment. Both sides acknowledge that mistakes could have irreversible consequences, and every experiment is monitored with extreme caution. By the time the colony reaches its 150th year, it has evolved into a fully functioning civilization with multiple generations born and raised entirely on Proxima B. New forms of governance, education, agriculture, and technology are designed around the planet's unique challenges. Despite the hardships, the spirit of exploration, innovation, and resilience endures. Humanity has not only survived beyond its birthplace, but has begun to thrive, demonstrating that interstellar colonization, once a dream, is now a reality. The colony's social and technological evolution continues at a remarkable pace. By the 200th year, the population surpasses 10,000 inhabitants, and the colony is no longer merely a survival outpost, it has become a thriving interstellar society. Vertical agricultural towers stretch like futuristic monuments, producing food, medicines, and even bioluminescent plants for illumination. Engineers develop materials using local minerals to construct radiation shields, energy systems, and durable structures capable of withstanding extreme weather conditions. Scientists study the native microbiome and mineral composition to identify sustainable ways to utilize Proxima B's natural resources without damaging its fragile ecosystems. Education and culture evolve alongside technology. Children born on Proxima B grow up fully immersed in an alien environment, yet maintain a connection to Earth's history and knowledge. Cultural expressions adapt to the dim twilight and alien landscape, blending music, art, and storytelling that reflect both the challenges and wonders of life on the exoplanet. Social structures emerge organically, prioritizing expertise in survival, engineering, and environmental adaptation. Governance systems balance centralized decision-making for critical survival issues with community councils addressing local needs, fostering cohesion and resilience. Medical and psychological systems remain a top priority. Long-term exposure to Proxima B's gravity, radiation, and atmospheric toxins requires constant monitoring and intervention. Advanced medical facilities combine human expertise with autonomous robotic systems to ensure the well-being of the population. Psychological support programs remain essential, with virtual reality recreations of Earth environments helping colonists cope with isolation, perpetual twilight, and sensory deprivation. Community events, rituals, and structured routines reinforce social bonds and maintain mental health. Terraforming efforts begin on a larger scale. Controlled experiments aim to modify localized regions, adjusting temperature, atmosphere, and chemical composition while observing potential ecological impacts. Scientists debate the balance between adapting humanity to Proxima B's conditions versus altering the planet itself. Ethical considerations remain at the forefront, as irreversible mistakes could endanger both human settlers and native life forms. Despite challenges, incremental successes build confidence in humanity's capacity to not only survive, but shape a new home in the stars. By the 250th year, Proxima B is no longer just a destination. It is a functioning civilization capable of long-term sustainability. Families thrive. Children are born and educated in specialized habitats, and governance structures maintain balance between resource management, technological advancement, and ethical stewardship of the planet. Infrastructure continues to expand. Energy systems, transportation networks, and habitat clusters interconnect to form an organized urban landscape capable of supporting tens of thousands of inhabitants. The colony represents a living experiment in human resilience, adaptation, and ingenuity. Even as the colony matures, the spirit of exploration persists. Scouts and robotic drones continue to map surrounding terrain, search for resources, and identify potential expansion sites. Scientific research focuses on both understanding Proxima B's environment and developing technologies that could eventually allow humanity to travel further into interstellar space. The achievements of the colony stand as a testament to centuries of ambition, perseverance, and the ability to overcome challenges once thought insurmountable.